Okay, welcome everybody to the first sort of in-person Astro seminar in how long? I mean, two years, over in 2 years. So you're a pioneer here, and we welcome everybody who's participating online. So our speaker for today is Xavier Prochaska from the Astronomy and Astrophysics Department at the University of California at Santa Cruz. You are such a Californian. You got your Xavier got his PhD from the University of California at San Diego, and then was a Hubble postdoctoral fellow at the Carnegie Institute, I guess, also in California. So Xavier's published nearly 500 papers. It has, I was shocked with a mammoth H index, over 100. Super, just incredibly productive. Xavier's research description on his webpage talks about research on gas in and outside of galaxies, especially in the early universe, but at least in the community, large fraction of which is here in the room, that studies fast radio bursts. We know Xavier as one of the leaders of the F4 collaboration, which is a wonderful acronym called Fast and Fortunate for FRB Follow-up, which uses leading optical facilities to study fast radio bursts in partnership with discovery groups all around the world. And he's here to tell us today about his work on fast radio bursts. Please take it away.
Thank you, Vicki. And thank you for this opportunity to give my first talk. Well, certainly my first seminar post-pandemic. I don't know if the 20 of you are the winners of the lottery or the losers of the lottery, but either way, thanks for your in-person presence, and thanks for those listening somewhere outside in the universe. Vicki's right. I've been in California for more than half my life, but I am an East Coaster, so it's nice to be on the East Coast. I grew up in Rhode Island. I'm told this gentleman used to be on the faculty at Brown. My father was faculty at the University of Rhode Island, and we did one road trip through this part of the world when I was about 10. So it's my second visit, but I don't remember the first. So it's nice to be here for real for the first time. Vicki also mentioned that I have been working a lot on fast radio bursts. I'm really excited by them. Hopefully, I know many of you already are because you're working on them too. But let me share some of that excitement for the rest of the crowd. A lot of that's in collaboration. Vicki called out the F4 logo here, or the team that is most of my effort. And we do partner with a number of folks around the world who do the hard work, really, the radio discovery for fast radio bursts. And most of the results I'll be referring to today come through our collaboration with CRACO, which is the FRB team on the ASCAP telescope in Australia. And if those acronyms don't mean much to you, I'll introduce a few of them as I go. Come on, there we go. Speaking of F4, this is most of the team. There's a few undergraduates not pictured. And Terne Takari, who I'm sure the FRB folks know well, is at Northwestern. She's part of the team too. She had her photo here. The old folk like myself are Wen Fei, she's not old, at Northwestern. Nicholas Tejos, he's not old, I'm old. And Regina Jorgensen, who's the director, you can't read it, at MMO, Mariah Mitchell Observatory. Who's heard of Mariah Mitchell Observatory? I see 3 hands, and Mohit's only got his hand. He only probably because I told him. Have you heard of it?
I've heard of it.
And where, sir, is Mariah Mitchell Observatory? This is your best observer in the room because he knows where the telescope, the observatory is at.
It's in New England and in Massachusetts,
Good.
but I think it's in southern Massachusetts, Cape Cod.
You're very close, Nantucket, where I was on my honeymoon. Regina is the director. He's basically the whole staff of that observatory. We share the same PhD advisor, Art Wolf, at UC San Diego, and now we work together on fast radio bursts.
So there's a takeaway on marrying astronomers, look out for a high moon at an observatory.
I'm not married to an astronomer.
No, the one that married you.
Something like that. It's a plug for Nantucket, I guess. Yes, lovely place. Okay, so I believe some of you don't work on faster. I know some of you don't work on faster overs. Maybe you've been to enough talks, virtual or in presence, to have heard enough about them to not need an intro. But let me give you a brief one anyways. These are some slides I've put together mainly for talk to my physics departments on the expectation physicists will have heard of gravitational waves, and in fact probably thought a fair bit about them, even if that's not the field they work in. So here we go. Gravitational waves, if you followed them, you've seen cool cartoons like this. They're the ripples in space-time that we can detect. Do detect with our experiments on Earth, typically typically always coalescing compact objects. Probably those are cartoon black holes. I'm not sure what the artist had in mind here. If you've been following the field at all, you know the detectors that they use are interferometers, these kilometer longish tubes underground with magnets and lasers, which is amazing. Took them decades to achieve the precision to now make detections. Compare that with fast radio bursts, where even oldish single dish telescopes can be sufficient detector to detect them. But as you'll see as I go on, we have new technology which is really driving the field. And interferometers often play a role in the FRB world too, as they do in gravitational waves. The signals have interesting similarities if you squint. This is the chirp of one of the first gravitational wave events detected at the two sites. And notice the time versus frequency plot. with a sweep. It's pretty amazing, really, if you think about it. Yeah. The frequency are hertz here, and tens of hundreds of hertz. Fast radio bursts. This is the first one published by Duncan Lorimer in 2007, which certainly grabbed my attention. Again, time frequency plots. And here the sweep is due to plasma physics, the propagation of the electromagnetic radiation through a plasma, which retards the arrival time of the lower frequency photons, giving rise to what we call a dispersion measure. Dispersion. We have strong reasons to believe, I don't know if you could say proven, that the gravitational wave signals come from coalescing black holes and other compact objects. That's certainly the theory, and the predictions one makes from that theory match the data exquisitely. So sure seems like a good model. Today, I think maybe if you pulled the FRB aficionados in the room, you might get several different answers on what the most common origin of an FRB is. Probably magnetars would be the top choice, the mode. There might be some disagreement on that because it's largely unknown today, I would say. Some of the science you can do with GWs, gravitational waves, are to learn about demographics, or some of the physics is right. A new probe of the universe, gravitational waves, does harken quickly back to compact objects and processes in the strong regime of gravity. With fast radio bursts, you're probably probing very strong magnetic fields in a plasma, perhaps relativistic, around a compact object. You get the short time scales that we see in the phenomena. And then maybe more coming to the thrust of this talk, both provide an opportunity to probe the universe in a unique way. Gravitational waves enable a measurement of the expansion rate of the universe. If you can determine the redshift of the source, I think everyone here understands redshift. Yes, you're astrophysicists. Then the signal plus that redshift give you a very precise measurement of H0. Even a handful will be amazing. And there are a lot of folks in the community striving to do exactly that. And with fast radio bursts, I'll impress upon you one of the experiments we can do is to weigh the universe, measure the mass density. And I'll actually come to an alternative measurement of H0 as well.
So is this
Towards the end of
mass
the talk.
density or baryonic mass?
Baryonic mass density. Absolutely. That sets the stage. Any other questions at the high level on FRBs? Okay. Part of the reason there are many students in this room working on FRBs has been the rise of the field over the last decade, or less. As I said, the first burst was published in 2007 by Duncan Lorimer. Here's again. I want to emphasize some of the, again, that dispersion, that sweep, the arrival time of the photons, the function of the frequency, A per squared. It gives this characteristic sweep. The width of the intrinsic, and I shouldn't call it intrinsic, the width of the pulse is much less than this millisecond or so delay across the passband. And this is some cartoon of it. But you or didn't put a scale bar or whatever on the graph. I think this one is of order millisecond in width. But they can be as narrow as even perhaps tens of nanoseconds, certainly microseconds. From that sweep, all the signal you see here can be used, more or less, can be used to estimate one number that I care about, many other people do, the dispersion measure, DM. I'll start calling it DM. And that's the path integral of the electron density, ordinary matter, not soft matter, weighted by the scale factor. When we go to cosmological distances, it comes into play too. That's where we were in 2007. The field, I'm just going to skip over a lot of the history of FRBs, which is lots of fun, I have to say. If you're coming out to dinner or wherever, perhaps Vicky, she knows even better than I do. There were many exciting things, including microwaves, that I'm not going to put this talk. But a phase transition in the field was the first localization, which came about by observing this repeating FRB, sometimes referred to as R1. I like to call it 2012, 1112, sorry, 1102. Those are a number of the pulses that were detected from this one fast radio burst, and that allowed the BLA to point at it and detect it and localize it to sub-arc second precision. Not shown was the error uncertainty on these pulses. Must have been like 10 arc minutes, something of that scale. At sub-arc second precision, you can localize the source to a galaxy, and then it's relatively straightforward. Take a spectrum of said galaxy and measure the redshift. And this verified what I think the field had largely come to accept, that these are extragalactic. Many of them, most of them, all of them are extragalactic in origin. What other technical advances have come along? I'm at the center of CHIME, I guess I would call it. Amazing experiment in Western Canada, which is mapping the sky for H1 as well. Something that excites me in other areas, but it's a workhorse, the workhorse of fast radio burst detection in the field. I'm sure you all are up to thousands. I've not asked anyone, so Vicky, you don't have to worry about them divulging secrets, but it must be of that order. Certainly 500 published, roughly. Most of which are augmented or poor localizations, but still wonderful for populations and much other science. Some of which I'll hint at today, but not too much. As I said, our team has teamed up more with this facility, which is ASCAP. It's a precursor to the SKA, the Spark Kilometer Array. Located in Western Australia, 36 dishes, and when used as an interferometer at these frequencies, can get to of order 10th of an arc second precision and localization. Maybe a few tenths. The rate of detection has been about 10 in the mode that where we're localizing has been 10 per year. And we're just completing an upgrade called CRACO. They are completing an upgrade called CRACO. Keith Bannister is leading that. That will increase the rate 10 times. So, order 1 week, if not a couple per week at that precision.
So what is the sky cover that ASCAP
I think it's 20 degrees, 20 square degrees. It's not big. 30, thank you. Sherry, how are you? Can I defer all future aspect questions to the, and about localization and polarization to the young woman from collaboration? At that precision subarc second, it's ideal for post-galaxy associations. Here's one example. This is from a student's paper with HST, a Hubble Space Telescope imaging of one of these FRB regions, 180924. And that's its host. At subarc second precision, well, at any precision, you can do a probabilistic association. At subarc second precision, we're finding that the majority, overall majority, are associated at above 90, 95% even confidence level to a single galaxy. And then my bread and butter spectroscopy, we take spectra of these galaxies, get the redshift, and measure other properties of the host.
But these are not repeating fast regulars.
Of the sources detected by ASCAP today, one is known to repeat. One.
Because I was just,
Two are known to repeat.
the reason I asked the question is that before you said that it was crucial for.
It was crucial for the very first one. In many ways, well, one might argue in many ways it's an oddball.
But how reliable is this correlation between optical and fast burst if you only have one burst?
I think you're asking how good is, are you asking how precise is the association of that event to that galaxy?
Yeah.
I'm happy to discuss that at length with you and have a whole other talk on it. And this, I think this one is at 99.9% given the priors of Bayesian analysis. If that works. And that's with no redshift information, no dispersion information, just position of the source and properties of the galaxy, observed properties of the galaxy, not much. And this is the paper if you're interested in that in depth. Or that's the algorithm of the papers. Agrawal et al. 2021.
Sorry, just,
Yeah.
I'm puzzled by something you just said, that the
Yeah.
properties of the galaxy?
Yes,
That was-
which goes into the analysis or the position of the galaxy. That's two numbers.
Oh.
The magnitude of the galaxy, that's observed, not measured and measured. Direct observable. And the angular size of the galaxy, also direct observable. And then the localization. Yes.
Okay.
So no redshift, no dispersion measure, no star formation rate, no.
Okay, so you say properties of the galaxy, I don't think of position as properties, but you're right, they are, so.
Okay, and as I stand here today, pretty much every large or even small radio telescope in the world trying to collect FRBs. So the field really has exploded. There's a whole bunch not even pictured here. Hence the rise of FRBs. This is a fun little figure I made on the fly. Blue are, FRBs drawn from the TNS, the naming. The aficionados know. This sudden flat line of 2019 is not because there aren't more FRBs after 2019 or whenever you all stop publishing, but it's just because of that. I mean, it must be a handful in there of these. And then the red is the localizations. So this exponential jump is CHIME. And this, by and large, exponential jump, it's CHIME, but it's mainly ASCII. And we're about to have a second jump in the localizations, for sure. CRACO and DSA will do that on its own. CHIME out as well. Okay, and I was told I'll stop at 45 minutes. I know people listening online often lose attention by then. Yeah. Okay. So we'll see how far I get. It's fine. What brought me into this field is this topic, me, myself, personally, was to use fast radio bursts to probe the universe on large scales, and to some extent galaxies on large scales too. I'll just talk about the second part. All right, so back to dispersion measure. You've seen that. Remind you, it's an integral quantity, which means everything in between us, or us, that's the sun, and the source can contribute. So let's start over here. It's easier. Around us, in our galaxies, interstellar medium, acronym. And the warm ionized medium almost certainly dominates the contribution to the DM of our galaxy. We have a dark matter halo. There's strong evidence from that for other galaxies and for our own. It has baryons in it. It contributes. We live in a local group, M31 is part of our local group, Andromeda. Within that, like the halo or coalescing halos, are additional baryons, electrons, they contribute. Then I lump everything out there into one term called the cosmic web. I'll call that cosmic contribution. That's both galaxies and stuff in between galaxies, what I call the intergalactic medium. And then any electrons around in the galaxy hosting the FRB and its local environment will also contribute. So everyone keep that in mind as I go through some of the results here. I'm going to focus on this, what excites me, well, at least in this talk, what excites me the most about FRBs. But in order to get access to this or make constraints on this, I need to have some understanding about the rest of this. You're welcome to press me on the soft spots. So I consider them a blessing and a curse. The blessing for me was I had been studying the intergalactic medium basically since I was a PhD student, and was largely ignorant of all the matter because we only could see the few nuclei that were neutral, hydrogen atoms. And all the ionized gas out there was invisible to us. And with fast rate bursts, it's pretty much the opposite. We're completely sensitive to the electrons, the ionized material, and largely basically insensitive to the neutral gas. But that's a pathetic amount of dense gas. Pretty pathetic amount in comparison, especially in the early universe where I was studying. So the blessing is we're sensitive to everything. The curse is that we're sensitive to everything. So doing the science means understanding the other colors in the gray. I was most motivated by what we refer to kind of casually as the missing baryons problem. Most of you have heard of that maybe now. It goes like this. We have measurements from the early universe of the mass density in baryons. More precisely, it's omega b h not squared, h squared. And it, yeah, I said I would do this. Who's still doubtful about cosmology? You're encouraged to raise your hand. Who likes to? I mean, I'm a naysayer. I really am.
In what sense?
Like the standard model is wrong, or something's just wrong about our cosmology. I was at UC San Diego with Jeff Burbidge. He thought the whole thing. I don't expect there's anyone going quite that far here. But this for me is as strong as this like puts it over the top for me when it comes to our model, kind of elementary universe expanding. And what is being shown here are two experiments. So the blue is an estimate of this quantity from deuterium measurements in the early universe. That's something I've worked on. Quasar absorption line again, deuterium. That's the blue swap. And the gray is another estimate from the CMB, cosmic microwave lines. Okay, two totally different experiments. One's at 7 minutes. Okay. One's at 300,000 years after the Big Bang. So both are early universe, but not at the same time. Totally different data sets. Totally different underpinning of astrophysics. This is Big Bang and synthesis. This is acoustic suppression of acoustic oscillations in a large universe plasma. Right? And they get the same. So perfect, very high precision.
What about lithium?
Lithium is part of Big Bang nucleosynthesis, but it does not play a role in this estimate.
But there's a problem with lithium.
There is a problem with lithium. I think there still is that in the literature of late. Almost certainly in the stellar measurements, not in BDM.
Okay.
But yeah, is there a course? But yeah, there's a problem with H0 and CMB.
Okay.
But neither, yeah, how much lifting in the universe plays no role in the blue. H naught plays a role in this one. So we've known how much, in this respect, we've known the mass density of the universe times H. So this is mass density of the universe, well, with a critical mass density involved, times H squared. We've known that for 20 years, this number. And what Fukugita, even a bit more, 25? What Fukugita, you can't read in the back, Fukugita, Hogan, and Peebles pointed out in 1998, when the Big Bang nucleosynthesis numbers were there, the CMB actually wasn't quite solid yet in 1998. Still coming. Nevertheless, they did a census of that quantity, omega baryon, how much matter, ordinary matter, is in the current universe, and came up short. So they counted up how many baryons were in clusters, how many baryons were in stars of normal galaxies, how many baryons, like yes, still normal galaxies, how much gas, atomic gas and molecular gas was in galaxies. So 21 centimeter observations, CO observations, just optical light of stars, X-ray observations with hot gas clusters. And that was it. And they came up a Pac-Man short, which was roughly 2/3 of the number. And that beget the missing baryons problem. And I spent 20 years chasing this problem with every telescope I could put my hands on. I'm embarrassed to say how many orbits of HST or nights of big telescope time. We added up the amount of federal funding, it would be embarrassing, I guess. A lot of the science, good science, I hope, was done with that effort, but still, we didn't succeed. This is where FRBs came in. Shortly after their paper, the folks down the hall from them at Princeton said, oh, we know where, we run models of the universe in our computer, we know where that gas is. And they invented a name for it, the wind, hot ionized medium. And the physicists or anyone, here's a phase diagram of the universe, density, temperature, interstellar medium, dense and cold. Gas around galaxies, not as dense, still pretty cool. Intergalactic medium, what I call the line off the forest, is cool and very low density. And then this WIM thing is hot and or warm. A million degrees is warm to you. This is the Earth, or hot to high. And this is very hard to detect in any of the techniques I had at my disposal for those 2 decades. And that's why I mean,
Okay, how do you know the temperature? So this
it's a prediction
from the
from the computer simulation.
Okay.
Sorry, that wasn't clear. Computer simulation.
this is a hydro simulation.
Yes, sir. With 1998, not that many Dolphin whistles, but most of the heating is gravitation. So there's some contribution from sources in the universe, but most of it's actually gravitational. It's actually pretty much anyone that runs a supercomputer simulation will predict a wind of some sort if they build structure. So there's a more modern version of a set of simulation. This is another simulation of the cosmic web. Very large scales here. The orange, the small orange things are galaxies. The big ones might be a cluster of galaxies. Okay, so where do fast radiobirds enter? They enter in right here. In that we have a very clean analytic, well, integral. I can write down the integral. I can't do the integral with an analytic formulation, but an analytic description of the average contribution of the universe in its dispersion measure that one should see in any source for us fast radiobirds. So that they didn't really only game in town. Depends a bit on cosmology. Hubble's constant. Omega matter is dark matter. Density of the universe, they go down to dark energy. But by and large, it's really just how many electrons you have in your universe. Some of the other equations that go into that. But that's a very clean prediction of what one should see for the dispersion measure of the universe for sources like fast radiobirds. Yeah,
Omega M there is not only dark matter, is it?
it's not only, excuse me, matter.
Sorry. Just wanted to understand.
showed my old age. When I first started worrying about omega matter, we had the baryons wrong by a factor of 2. So they were even less important. And we had omega matter by, another 5 or 10%. They really didn't matter. They do. So this is what, there's a way to get rid of that. Look like I did too many down. Seen it, there it is. Escape to bring it back, okay. So this is that equation is the black line, given our best estimates of these numbers from the Planck experiment on CMB. And this is what happens if you increase the dash, is if you increase the mass density by a factor of 20%, or if you change Hubble's constant by 20%. Those are the dependencies as a function of redshift. You see there's a fair bit of power in that measure. And so we set out to do this experiment with ASCAP primarily, first publication only. I'm interested in that quantity. We measure that quantity. And I guess the blessing and curse is all these terms can and do contribute to the observed number. We have a pretty good model of that quantity, enough so that I'm willing to check it off and not worry about it. This analysis, at least not today. But these we don't. And that remains a soft spot in this analysis. Keep that in mind. So just in this paper I recorded all I'm about to show you in 2020, we assumed a simple scalar for the halo of our galaxy. And 2 numbers defining a log normal PDF for the hosts and fit for those, marginalized over them. And voila, what is now referred to as the McCord relation, named after J.P. McCord, who had an untimely passing like 2 weeks after publishing the paper in Nature. He was one of the leaders of the ASCAP project, and certainly leader of the paper. You're to be impressed that the colored dots, which are 5 dm estimates of the cosmic, as I just described it, versus redshift, which we measure from the host galaxy, that it follows the predicted curve for dm cosmic in our universe. Enough so that when I gave this talk in front of Masataka Fukugita, my son in Tokyo, he agreed that we can stop worrying about the missing variance problem that he launched in 1998. And do other things, which we are. When you do a full forward model and Bayesian analysis, that's our estimate for omega b times h, which is what FRBs are sensitive to, not omega b h squared. And the dash line is what you would estimate from CMB. You are in good agreement. What are we doing now? So the rest of my time, good 10 minutes, I'm going to talk about what we're up to today. One of these, still in the context of FRBs probing the universe on large scales, we're improving the methodology because we need to over what was published in McCord 2020. In fact, Clancy James has published 2 papers on this. If you're in the field, you've probably seen them. Just came out a month ago. To do this properly, to build one has to build a better forward model of the FRB experiment. That means the host dispersion measure, which we already had included. The energetics of FRBs, they play a role here and are unknown. I was for sure doing a better job, I'd say, explaining that than anyone else. So let's call that largely unknown. The FRB intrinsic width and scattering plays a role. Your telescope has, of course, part of the experiment plays a role. So modeling the beam, the sensitivity matters. And we're about to submit a paper showing what we think one can do with Hubble's constant today, which is not much. Show sort of preliminary results on that, but something. why H naught, well, how H naught, maybe is the right question. I hope I impressed you that omega BH squared is known. I'll go to my grave on that. 2 experiments, same result, same number. I'm sure of that. So, and I should add probably a slide. For fast radio bursts, we have a constraint on omega BH. Omega BH squared is known. Omega BH is what fast radio bursts get you. Take the ratio you have, estimate on H naught. Constraint on H naught. And if you adopt, and you should, the prior of that omega B H naught squared is known, then this is the dependence of the McCoy relation on redshift. And it's counterintuitive. What I've shown here is H naught increasing blue to black to red. H naught is increasing, the relation goes down. Since I told you omega B H naught is what FRBs care about, you say, well, why? Because I held the omega B H naught squared fixed. So omega B is going down. Anywho, what you're to be impressed upon is this is the power one has in measurements of the extragalactic contribution to the DM, which we can estimate pretty well with the host included and redshift. And so by filling out that plane with measurements, yes.
I don't understand, why is it 2 double values? No,
Sorry. So yeah. I skipped over a slide. I'm not going to skip over it. Didn't dwell out long enough. Sorry. Let me go through this figure, which I didn't say much about. Redshift, DM extragalactic, which is the observed number, known very well, minus the Milky Way's interstellar medium, known pretty well, and a guess at the halo, known pretty well. You good with that? At this stage of the talk, we're going through aficionados mainly.
Okay.
So it's host plus cosmic.
Right.
Got that?
Yes.
Good. The color is a forward model of that distribution for ASCII. In that forward model is all this stuff.
Okay.
I have, I can tell you the values taken here. They're value, sensible values, but certainly not the right ones. So there's uncertainty in all of them. The black dots are a realization of that model under random draws. And the contours, then that's what I'm plotting in the next slide, are the 90% value. 90% of the 100 FRB should be in the dash line.
That's the missing thing. It doesn't curve back. That's a contour of the next plot.
Correct.
Okay, and those dots are not data points.
These dots are a random 100 points.
Okay.
I'm sorry to get this.
I was like super impressed, actually.
Today there's 16. I won't show you the plot. Well, 16.
And the thing missing in the contour is
Yeah.
that this distribution is highly peaked along a straight line.
Ooh, that's very good. That's clear here.
Well, yes, that's the whole message there, right?
Yep.
Okay.
So almost all the constraining power comes right here.
Okay.
And that, in the way, a way to think of it is a host has a long tail to large values, largely unknown. And then your galactic medium has a large tail, a long tail to large values, also not so well known. So most constraining power comes here. All said. Back of the room. There are degeneracies as well. So I'm showing what the degeneracy is, say, with the maximum energy of the FRB population assumed. And that's the dotted line. It's not fully degenerate. That contour is not the same as any other contour, but there's clearly, it's not degenerate, but there are degeneracies. So if that were the experiment, what would the constraint on H naught be? Something like this. Was a forecast for what 100 FRBs might give us localized. Yep.
How much better would 1,000 FRBs localized be?
At what number does it change over to pure systematic?
Yeah, that's the right question. Now I'm trying to. That's why I'm talking.
Is it already there with 100?
For sure, 100. No, it's not. Well, I'm not including systematic on FD.
Yeah.
I have not included in this modeling what we call capital F, which is a parameterization of the IGM scattering, not known today.
You're already there with.
You're gonna hit the system. I don't think we're there with 100. I don't think there's a systematic that dominates over this width at 100. But I think at 1,000. Yeah, I don't think so. This is what, that's a 10% measure? 1 second. I don't think there's one at 10% in the systematics. At 1 second.
So what was the answer?
That's a forecast.
Yeah,
Where we are today is we haven't finished the likelihood cube, but this is about what you'll see in the paper. Imagine another half of that. Not impressive,
okay.
not competitive, but realistic. From 16.
No, but the question I didn't get the
Ah.
answer to was if there's 1,000 and let's say
Ah.
you didn't hit the systematic limit.
Oh, well, it should be root n. I used to say it should be root n, but of that order. So 10% would be a 3%.
3%.
You're not, well, we're not going to get for sure 3% you're getting systematics. There are systematics I worry about at 3% level for sure.
Okay.
I can't think of one. Well, I'm not sure there's one at 10%. I don't think. Okay, I'm gonna wrap. Should I wrap up now?
No, it's okay. I think you're good. I don't want to speak for everybody, but I'm fascinated.
I'll go 5-ish more minutes, but I don't want to overstay my welcome. What's the phrase? Okay, so the other thing that I get really excited about with fast reverse in terms of probing are galaxies. I have worked a lot on galaxies, I guess. Here are 6 of the host galaxies. The aficionados will not recognize 5 of them because they came in 2021 and aren't published yet. But there's of order 10 from 2021. These are 5 of them. That one you might know. You should know if you're in the field. What can one do with well-localized events on galaxies? Well, you can measure the galaxies, fine, we do that. Learn about the demographics of the galaxies hosting FRBs. This is published. These are 19, I think it was something like that. Host galaxies from Bandari et al. Last year. And I'm mainly showing this plot. This is comparing luminosity of the galaxy and its color, where that's up is red. And the gray histogram in the background are a random sample ensemble of galaxies on the sky. And you're supposed to be impressed that to 0th order FRBs track normal galaxies with probably an under representation of the redder population, but mainly normal star forming galaxies. That's cool. When you then are excited by interstellar medium.
Sorry, can you go back?
I may.
Why there is such a large color excess? Or
Oh,
even low redshift galaxy?
I don't remember. I'd have to look at the individual source. Probably Milky Way extinction. The Milky Way obtained. But we could look at it. Humans always are attracted to big error bars. Yes, ignore those.
No, I just think like you're in all that power quite small for nobody was there.
Yeah, I don't. Okay, so in the signal of fast reverse, if you have the technology, which most experiments do, is the ability to measure the rotation measure, so the change in polarization with frequency, and that relates to the integrated magnetic field along the sightline, with some scale factors as well. Again, it's that curse and blessing. You're sensitive to all the magnetic field along the sightline. Here, one has expectations that our galaxy and the host galaxy should know. Intergalactic medium will matter, but our current expectation is small. So it's our galaxy and the host. So we have of order 10 well-localized FRBs with RM measurements now. Not quite there, not quite 10. And Alexandra Mannings is finishing up a paper studying those. And part of that analysis, this figure's too much. I'm going to skip that figure. Part of that analysis is to compare with those that build galaxies on computers, so do galaxy formation science. And that's just shown here. So it's also a little complicated, not too bad. When the purple are the modeled from rotation measures for galaxies with the same properties as these galaxies. So our colleagues went to their computer printouts, and matched by stellar mass and other properties of the galaxies with their computer galaxies. And they had magnetohydrodynamics as part of their code. They made estimates of the rotation measure. And by and large, they're overestimating, not in every case. This is R1, which is crazy. Overestimating the rotation measure in their made-up galaxies compared to the real universe. Takeaway points. So their model is wrong. That's that's a driver of the interstellar medium and other properties of the galaxies. It's an important result. Last but not least, I want to use FRBs to probe intervening galaxies. Here's the poster. Well, we'll call it that. There's an FRB, there's a galaxy in foreground to it. And we can use the signal. Let's zoom in. FRB at this redshift. Another galaxy close by in projection, but not close by really, because its redshift is much lower. So we're probing the outer parts or even the halo of that galaxy with the fast radio burst signal. One gets two measures. I'll skip that slide. Who's that? That's Matt McQuinn. Who's that? Sherry did. I don't know what did you take that from?
That was at Green Bank. It's the paper dish.
So, as part of her thesis, she measured at very high time precision a number of the ASCAP FRBs, fast radio bursts, and 181112 was one of them. Thank you, Sherry. And that placed a upper limit on the intrinsic width of the signal, which lets us put an upper limit on the density of the gas that it's transmitting through. This is something I've worked a lot on halo gas. This is not a measurement we can ever really make, density. So this is a new constraint. And similarly, rotation measure gave us a constraint on the magnetic field. And so for this one halo, we ruled out the hash region. This is density and magnetic field that's not allowed by the data. And in neither case could be, there's no other real approach to measuring magnetic fields. Very challenging at least, or density in halos of gas. So another aspect of FRBs that really excites me. Okay, the last few slides. Sunil Simha and KG Lee with Flim Flam are going to town on measuring now where are those missing baryons. They're no longer missing. You know they're there. We detected them. Where are they located more precisely? And see their papers on how that's done. I know there's an effort. Speaking of Mahmoud about that today. I think there's an opportunity to learn a lot about the local group. Trying folks, please measure M31 at your earliest convenience. I think you have enough signal today. Do it. Or if you need the data, I'll do it. No, do it.
Wait, what exactly do you want us to do?
I want to see the density profile of the halo of M31.
Oh, so you want us to look for FRBs that are near M30?
Yeah, I'm sure you have them. I know you have them. You already published some. Do a differential experiment to measure the density profile of M31. The halo. Would be really amazing. Yeah.
You mean bring them closer?
You're basically just doing a cross correlation analysis in the center. Think of it that way.
So we get a fast radio burst trace the mass.
No, you're just using the dispersion measure. I didn't say dispersion measure. I thought that was obvious. Sorry. You're using the dispersion measure.
Oh.
Cross-correlating dispersion measure of the FRB with the center of M31. Simple experiment. I can't wait to see Amanda's work on the halo of the Milky Way. That's something many of my colleagues and myself have worked on through other approaches, which don't work very well. FRBs are great. Data, okay, and I'm done. I think I said everything here, yes. Thank you for your time, thanks for coming. And, appreciate it.
Do we have any, we've been peppering you with questions, but let's continue that enjoyable process. Any questions for,
We should also ask for questions from the chat
right,
for people on Zoom.
I can bring that back.
No, I have someone who's sending me the.
Oh, you have
questions. So I just want to make sure that people on Zoom know they can ask questions.
Yeah, absolutely. We have a question over there.
Earlier in the talk, you put a green check mark over the.
Oh, yes.
weight contribution.
Yes.
Is that a blanket statement or is that specific to a given measuring field? Maybe.
Oh, I see what you're saying. Yeah, that is a blanket, yeah, I'll answer it with a yes to both. It's a blanket statement of galactic latitude of, I don't know, say 30, 40 degrees, where the end is now down to 50 or less. Yeah, through the plane, forget it. Don't include the analysis. That analysis.
Alice?
Yeah, this might be a fairly trivial question, but when you were talking about constraining H0 and you were talking with Matt about the systematics, what specific systematics are you thinking of there?
Yeah, let's give Matt the opportunity to press me further on that. He may have thought more deeply than I. It's quite a number of hours I have to into this. I'll point out the one that I know is a floor that may be very hard to ever's a long time, but deal with it. That's this number. Oh, so I didn't mention it in the talk, so I'll say it now. So FD, that's my way of saying the fraction of diffuse, deeper diffuse gas in the universe. Baryons. Right, so that's everything that's not us, the desk, or planets. Sorry, planet folk. We don't care about you for this. Or stars, or atomic gas, or molecular gas. Or remnants, neutron stars, white dwarfs, that came from Baryons. All right. So that's a lot of components to worry about. Most of them don't matter, a couple do. There are good experiments to trace those over cosmic time, and so we've included that in the analysis. But there's a systematic there, and the biggest one, oddly enough, is the stars. Yeah, the initial mass function of stars, IMF, which could be as big as 100% error on that number. And that matters. So that's a systematic floor that I imagine we'll hit with 1,000. I'm not sure it's quite 2%. It's up in that order. I don't know if I would call it systematics. Maybe, yeah. What do we call it when we have the incorrect model? All right, this is a model. For example, I've got a log normal PDF. I know that's not right. That's systematic. I don't know what we call that, but there's a floor there too, and how well we model the physics of this, and we don't model. I mean, we're not going to model FRBs from first principles. So, but
How do you know that that doesn't affect you at the current level?
how do I know? Well, how do I know? Because that's my current level. I don't think it's affecting me at 30%. How do I know? I don't know. I mean, I guess I would say to you, Vicky, look at the range of things we've modeled, and do you see a spot where it's 100% error that will then lead to a 30% error? So, and maybe there is. Probably not. Yeah. I would give Matt the chance to.
Well, are we having the people online going up?
There are no questions.
Oh, good. So we talked about cross correlations, and you mentioned N31. Cool.
Yes.
Lots to do there. There's also a cross correlation result of the catalog of FRBs with large scale structure, and the results are a little surprising, perhaps, in that very high DM sources seem to be cross correlated with structure at relatively low redshift, which, had that result come out before we knew anything about this relation, would have cast some doubt on how feasible it is or was or would be. Given that and where that excess DM may come from and what we're talking about in terms of post DM and so forth, shouldn't I already be a little terrified that, you know, when we put this forward as precision, as a key to precision cosmology, that some of our precision may still be lacking? We talked about systematics, but this is just basic assumptions that go in.
Yeah, so you're asking, do I worry about DM host? Of course. Do I think we can model DM host at 3% level? Probably not.
And in relation to the cross correlation, like what's going on with that cross correlation?
What's going on with Mahmoud's paper?
Sorry, yeah. From your perspective, as someone who believes in this relation kind of religiously.
Yeah, I think I'd have to read the paper more carefully. Answer that sensibly.
So there's a paper where we cross correlate FRBs with known galaxies, and we don't say anything about which one goes where. And there's kind of a surprising relation where the highest dispersion measure FRBs are correlated with structure that's relatively close to us.
Right.
Close on this scale.
And so that's,
And we could just be wrong.
that's expected for ASCAP 2.
Yeah. Yeah, it's
So
not
I
zero.
guess my zero response is I'm not surprised.
You have to give us a selection function that's weird before you can pull that out.
Well, now we're in the details of the paper, I don't know. But if you were to tell me that the highest dispersion measure sources are at low redshift and related to structure or DM host, I'd not be surprised.
That there was,
Yeah.
there was one of the plots showed like a part of that that went to.
So for the current system of IC, what we call ICS ASCAP, we should not be detecting hardly any 1,000 DM FRBs at redshift 1. If it's 1,000 DM, it's going to be either nearby structure and or the host. So I guess I'm not surprised by your result, but I don't know CHIME's sensitivity well enough to make a plot like this. You guys do, so make sure, you should make that plot as well, and make sure you understand.
The person in question.
One thing I want to mention is that the tail is very sensitive to your prior assumption on post-game distribution.
Yeah.
That log normal distribution.
Yeah.
So the statement that Matt made about the fact that most of those simulation points are at the bottom, I mean, really don't know where the tail goes, right? It's
No, that doesn't change this sharpness. Because eventually the DM host is 0. So it's as sharp as it gets. Right? Yes, it changes how tall that gets. It's already tall. Not this.
yeah, but like how fast that tail falls off. Like,
Okay, but you already have data. You already know to some extent. It's not. We're not.
we don't have many data points up there, like at IBM, right? So
Yeah, we know it's a tail. That's my point. We know it's a tail already. I don't care if it's a 1% tail or 2% tail for this chart.
No, I mean, we know we don't have redshifts for enough of them to.
I do.
plot this thing.
I have enough to know there's a tail.
Not the difference between a 1% tail and a 1% tail.
That's right. 1 and 2, I don't know the difference. 1 and 5, I probably don't know.
1 and 5.
But again, that's not going to affect the chart. That sharpness is because eventually you've got the Milky Way and you've got no DM host and you've got just DM cosmos. Okay, we probably lost most of the audience. But that was useful.
Vishwani has a question.
So could you go back to that slide which has the average DM cosmic?
This one?
No, the formula.
Ah, yes, of course. That one, let's go. Oh, I prefer the cosmic web version. Yes.
Yeah. So to be able to constrain the Hubble parameter or the Hubble constant by using the DM versus redshift relation, we will need to know the number density of electrons.
Ah, but we do. We know this exactly.
Oh, we know that.
Yeah, that's omega b h naught squared.
So we just use, that factor in that whole term.
Yeah,
And he's pointed out that the other factors are.
we know that exactly.
Yeah.
Well, 2%.
Yeah, I think I have the same questions, just to go back to the formula.
I mean,
So, yeah, that's very basic question, so it's not working in the field.
it's okay.
So this number density of electrons is a number density of free electrons.
Yes, sir.
Right.
And that's where this FB came in.
But,
Yep.
uh,
And then I should say, this is also known exactly from CMP. So don't worry about that one either.
So now, the crazy pencil and paper physicist comment is, if you could do this measurement of redshifts between 10 and 20,
Oh, boy.
you could maybe get at the F, which is the right. F.
Yes, by redshift 1, I would argue, and I think be correct, that FD is already 90%. Actually, sorry, 90, almost 95%. Ionized, 5%. Not diffuse. And by redshift 10, it'll be 99.9%.
You like to see that number.
Mhm. Well, okay, then you're programming ionization. So, sorry, at redshift 10, you might be back to neutral universe. But let's not start that conversation.
Are there any questions in the chat?
I just asked Adrian, but I don't see anything yet. Yeah, no questions.
Go ahead.
No, you have a question to ask?
But you have priority because you're working.
So X, I'm interested in that relation with the law. So the one that values.
The bar chart? That's a little bit overwhelming.
So you made a comparison between 5 FRBs, yeah, that one.
Yeah,
So what I'm thinking, I understand you said that you use maybe the hydrodynamic simulations and all, but it is quite well known that these simulations are really not sensitive for scales which is less than 1 parsec.
absolutely not.
And in that scales, we have supernova elements and all that. And we already know that that can cause rotation which is in excess of around 10 to the power 4 or 5.
So you are giving me exactly the arguments that my colleagues have given me as to why they're modeled wrong.
But I'm just saying that it's like actually, I'm just thinking about the idea of using
Yeah.
FRB rotation visual excess to say something interesting about the global property of the galaxies.
With enough statistics, yes. With enough statistics, yes. Right. I didn't say it explicitly, but as you know, we know where in that galaxy this thing occurred, pretty high precision. Right? So we have some sense of where in the ISM we are. We have, in this case, well.
But in 2D, and actually,
That's okay.
we don't know whether
That's okay. I'll know systems that definitely occurred near H2 regions or in projection near H2 regions, and some that won't. So you build up enough statistics, you'll be able to do some pretty cool differential experiments on what's the RM like in the ISM of galaxies as a range of the properties locally within them.
So I'm no expert there, but we saw this paper in 2020 where they used latitude dependence and they saw that there's this fluctuation in our, people think that maybe there's a turnover in the rotation measure.
In our galaxy?
Yeah, in our
Okay,
towards
yeah.
the epicenter.
Cool.
And when one of the plots, they show that the RM change just within few degrees is like more than 100 units. And that was a sort of alert for me, like, what do you call it, question mark. Even in our own galaxy where we don't see a very dark, very dense regions and all the molecular charts, we can see such high fluctuation that we're using 6 or 10 or 20.
I think you're saying galaxies are messy.
Exactly. That's right.
And so tread cautiously on.
And the
on-
worst
on
part
this.
is RMS
Yeah.
can be additive or subtractive.
Totally, all good points. I don't think those are enough to say don't work on RMs. But all good points.
I love your opinion.
I have a question too, but I believe by the argument you presented. You
Just so We harassed you a little bit about statistics and when the systematics take over. For the systematic you were first worried about.
Yeah.
You know, it doesn't help that much to have a lot of bits. For the systematics, I'm gonna call the host contribution a systematic.
It is.
The ones that I'm worried about though, you win eventually, don't you? I mean, you get to 100 events, you're systematic dominated, but then when you get to 1,000 or 10,000, you start to be able to measure the difference of this by having 100 events at the same redshift with different PMs and so forth. And then pretty soon,
I'm gonna
you
restate.
turn the whole thing around.
I totally agree with you. I fully agree with you.
Well, do you have an intuition of when that happens? Is it
And it comes back to this, they're a blessing and a curse,
okay?
right? They really are. Because other experiments, like you all are working on this, like as I said, I'm interested in this, but
Yeah.
you all are gonna have a great measurement of this soon. And then that'll be one less thing for me to worry about, right? And then we'll start knocking down, and then, all right, GM host is always gonna get challenged, but if we're lucky, there'll be some ugly thing like the Phillips relation where the mass of the galaxy or some property of the galaxy correlates with blah, blah, blah. There'll be something that will improve that, I hope.
How would you recalibrate that?
As long as there's no evolution, you're kind of okay.
If I had 1,000, I mean, in the make-believe world that I will never live in, that I had 1,000 FRBs at the same redshift, I can calculate.
Yeah, that's.
I can take out,
Yeah.
I can take out the impact,
Okay,
right?
In the make believe world,
I was actually asking if they're real world.
Well, you might also turn on gravitational lensing for just a few of those to learn something about the
Mm.
as well, the deep cosmology feature.
I have one from the chat.
Oh, good, good.
Okay, so this is regarding Robert's question. So then the problem is that if you're at high Z, where you're at 99.99% diffuse matter, then the probability of finding non-diffuse stuff with an FRB to do the science is very slim.
There's no FRB. Fair point.
Sorry, Robert.
I'm disappointed.
Well, I do have one more question, but it's late and I'm going to dinner with you, so maybe I'll hold it.
That sounds fun.
So I think we should all join together and thank